Hello, students. This is Unit 12 Notes, Section 1230, Permutations and Combinations. I'm just going to go over these quickly to help guide you through the notes. You can pause this at any time if you need to pause it, or you can speed it up. So the first thing in our warm-up is Holly, Tia, Kenji, and Nate all running for president and vice president. And it says Holly wants to be an officer with her best friend Tia. How many outcomes make up this event? And so when we look at our outcomes, we have Tia, and so Tia's row right here, and um, we also have Holly's row right here. So our two possible outcomes that we see in this list are TH and HT. So there are two possible outcomes of the way president and vice president could be awarded to just these two people. How many outcomes show Holly as president and Tia as vice president? And that's only one possible outcome because order matters here. We have president and vice president. So Holly as president and Tia as vice president, that's our HT. Generalize, how many outcomes have only one of them as an officer? So here, Holly, there are some possible options. When we start to look at Holly, we can have Holly with Kenji and Holly with Nate. So what we start to do is we start to cross these off, and as you noticed, I crossed off these options, and then Tia, same thing. Tia can't be with Holly or Tia, and so we have these two. And then if we look at vice president, we could go Kenji and Nate as president with Holly as vice president, and then same thing with Tia. So there ends up being 8 options. So we can cross off all the ones that are not options, and there's a total of 8. So what we're talking about today is permutations and combinations, along with the fundamental counting principle and this idea of the factorial. So there are two different things. There are permutations, and that's when order matters. So for instance, let me say, let's say I have 10 sailboats, and of those sailboats, 3 of them are going to come in first, second, and third place. Well, the first option, there are 10 sailboats. The second option, there are 9 sailboats. And the third option, there are 8 sailboats. So there are 8 sailboats left. So there are 10 possibilities for first place. Then for second, there are 9. And then there are 8 for third, leaving us with 720 possible outcomes. Well, this is what we call a permutation. And we use this notation, NPR, where 10 represents the possibilities, the number of items in our list, like sailboats. We're going to permutate them with 3 choices. So first, second, and third place. So that becomes 10 factorial over 10 minus 3 factorial. What is a factorial? A factorial is when we do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, and that's what the factorial means. It means continue on until you get down to 1. And 10 minus 3 is the number 7, so we get 7 times 6 times 5 times 4 times 3 times 2 times 1. And so this ends up becoming 10 factorial over 7 factorial. And what we notice is we can cross out all of these because they divide each other and turn into the number 1 for each option. And we are left with 10, 9, and 8. That's our sailboat example of possible permutations, which if you use a calculator, you would notice that 10, on your calculators, if you click the math key and you go over to the option probability, you can find NPR, you can find CPR, NPR, NCR, and you can also find the factorial key. I believe this is the second number, the second item, the third item, and the fourth item under our probability. And yeah, so it's N minus R. I don't like that they use the number 3 because 6 minus 3 is 3, so you can't really see where the 3 is going. So I showed an example here where 7 pick 2. 7 permeate 2 would be 7 factorial over the difference, which is 5 factorial. All right, let's say in that same example, the sailboats, all finish at the same time. Wow, a three-way tie. Well, that's a little bit different. That's what we call a combination. So 10 sailboats all finish, three finish first. Probably can't happen or won't happen. Finish first. In that example, though, we're looking for groups. So C, I think of as a group. If you hold your hands out and you make a big C with your hands, you're grouping everyone together. Combination with that group is what we call three, whoops, 3CR. So we'll do 10C3. So that will be 10 factorial over, oh, look at here. It's now R factorial over N minus R. So R factorial and N minus R. So all we're doing is dividing out the amount of groups of three that we have. So we have 3 factorial, and then we have 7 factorial. In an effort to save a little time, let's just copy this from over here. All right, I'll erase these. Oops. So the same thing happens, except we also divide by 3, 2, and 1. So it will be 3 times 2 times 1 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So here we go. We get all those go away. We have 720 over 6. Now you could have simplified these a little bit more. Like if I wanted to, I could just go 9 divided by 3 is 3. Then I get 4. 8 divided by 2 is 4. The 1 goes away as well. So we're looking at 10 times 3 is 30 times 4 is 120, which is 720 divided by 6. So we're at 120. All right, so it's the items, the groups you're looking for. So you have to think about groups. So if I'm talking about, let's say I have 8 books and I want to put 3 on a shelf. Well, that's going to be a permutation. But if I say I have 10 and I want, let's say I have 10 books and I don't care their order. I'm just going to throw the first book on the shelf, the second book on the shelf, and the third book on the shelf. That's going to be a permutation. But if I said, hey, I have these 8 books and I want to put them in groups of 3 on the shelf, like how many different groups of 3 can I make? And order doesn't matter. So it doesn't matter which one goes first, which one goes second, which one goes third. I'm grabbing that group of 3. How many possible groups do I have? Well, that's a combination. It's 8C3. And that's really what you have to determine is this a permutation? Does the order matter? An arrangement of items in which the order of the items is important, or is it like a group? So in the classroom, let's say there are 24 students. If I care who gets president, then who gets vice president, and then who gets secretary, if we were voting on a class president, vice president, and secretary, that would just be a permutation. But if I'm interested in, hey, what group of 3 could run this entire place? I don't really care where we put them in their position. Let's just get 3. How many possible groups could we appoint to positions that you'd be focusing in on a combination? The last thing is a fundamental counting principle. It's a simple idea where we just take something like a pizzeria, take a large and a medium, a deep dish and a thin, and a sausage, pepperoni, and cheese. Well, I can pick a large or a medium, so boom, that's your 2 sizes. Your 2 crusts are deep and thin, and then sausage, pepperoni, cheese are 3. You just multiply them together, you get 12. If you think about it, you can make a large and a medium. Each large or medium could be deep or thin crust, and then each one could be sausage, pepperoni, or cheese. And it's like a tree. You can make a tree with this. So there's 12 different pizzas that you can make. Well, they're technically permutations. They are 2 sizes, permutate 1, 2 crusts, pick 1, and 3 toppings, pick 1. So it's really 2 factorial over the difference, which is 1 factorial, 2 factorial over 1 factorial, and then 3 factorial over 2 factorial, which wipes out the 1, and we're left with the 2, which wipes out the 1, left with the 2, and wipes out the 2 and the 1, and leaves us with 3. So counting principle is when we group everything together. And we keep it simple. Two, two, three. Same thing here. Cars. Three trims, two transmissions, eight colors. Multiply them together, you get 48 options. Again, they are permutations, but it is much more simple that these permutations can just be multiplied together. To fully explain permutation, combination, and the fundamental counting principle, we talked in class about a pretty good example that incorporates all three. Let's say we go out for breakfast, no, dinner, and you have a appetizer, a meal, and a dessert. Well, if there are 8 options for an appetizer, 10 options for a meal, and 3 options for a dessert, that is 240 options of ways you can order an app, a meal, and a dessert. 8 times 10 times 3. Okay. Well, let's say it's actually your birthday and we're not getting an app or a meal. So that was the fundamental counting principle. Let's say we're only getting dessert and there are actually 10 of them on the menu. Then if we pick any group of 3, I say, hey, pick any 3 you want. That's going to be a combination because you're like, well, I could get the molten lava cake, I could get a cannoli, and I could get what else? Ice cream sundae. And so it doesn't matter the order in which they're delivered to your table. I'm just letting you get any 3 and you're grouping them together. So that's a combination. But a permutation would be, hey, not only do I want that ice cream sundae, but I want it to be first. And the cannoli, I want to exactly be second. And then, and wait, we said sundae cannoli. Oh, and molten lava cake, third. That particular order, there are actually, that's actually a permutation because it's specific to the order in which they're arriving. So there are so many other things I could have done. Maybe there's a cupcake and other items. And so if we're not only focusing in on the group that you're getting, but the order in which they're being delivered to the table, that would be a permutation. All right, there's a couple more examples I have here. So how many different ways can Gabriella make a playlist with 3 of her favorite songs? And that's going to be 6 different ways. All right, ABC, BAC, CAB, ACB, BCA, CBA. So it's 3 pick 3. What I haven't shown you yet is that this is pretty cool. 0 factorial defaults to the number 1. It's just the way we approach it. 0 factorial will be 1 because there's no way to do anything else and we can't divide by the number 0, so we just default it to 1. So 3 permutate 3 is 3 factorial over 0 factorial, which is 3 factorial over 1, which is 3 times 2 times 1, which is 6. Gabriella wants to make another playlist using 5 of the 8 songs. Well, so here she's picking 5. Order matters because it's a playlist, and the playlist literally has a spot 1, a spot 2, a spot 3, a spot 4, and a spot 5. It doesn't say, hey, she wants to pick 5 songs and she doesn't care the order. This is a playlist and order matters, so it's a permutation. Gabriella's 4 favorite songs. Ooh, she has 24 options for those because this is how many possible playlists are there for each situation. So she's picking her 4 favorite songs. And so it's just saying of the 4 favorite songs, how could you list them? 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 3, 2, 1, 4, 2, 3, etc. All right. 5 of the most popular 10 songs. Well, now we're looking at a group of 10 and we're picking those 5. So our permutation leads us to 30,000 possibilities. Now we're on to, we have 2 more quick examples. Combinations. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible summer camp activities. Now, if I want to do 3 of them, I could do climbing, cooking, fishing. That's going to be 10 times 9 times 8, where order matters, but not in the event we're doing a group. She can choose, Marisol can choose 3 activities for her session. How many different combinations of 3 activities are possible? So we're not saying, okay, You can pick one at random, pick another one at random, and pick another one at random. How many different ways, based on these 10? We are saying that the order doesn't matter of the activities, it doesn't matter where we start or end, and so the combination leads us to be, we have 10 factorial over 3 factorial, and then the difference, 7 factorial. You write those all out. The 7s, 6, 5, 4, 3, 2, 1 will go away. We can just write 10, 9, 8. Then we also have 3, 2, 1 that we have to count for, and that ends up being 120. Again, all this can be done in the calculator. You can type in 10C3 to the calculator, and you will get a result of 120. How many activities can a camper choose? How many ways can a camper choose 5 activities from the 10 available? 252. Same idea. I haven't finished this one, I guess. Okay, so use permutations and combinations to find probabilities. But in an effort to save time, let me see if I can pull it from a different year. Okay. A teacher chooses 5 students at random from the names shown to work together on a group project. What is the probability that the 5 students' names begin with a consonant? So there are total combinations are here. We have 8,568 total combinations because there are 18 people and 5 of them are, we're choosing 5 students. The combination of names with consonants, there are 13, and we're going to choose 5 out of that. The combinations of names without a consonant, looks like 5 choose 0. There are none. And so what we're going to do is we're going to multiply the probability of our combinations with consonants times our combinations with non-consonants. We're going to divide that by the total. And so it looks like these two multiply together. So this is irrelevant, really. It's just the number 1. So it's the amount of names with consonants divided by the total, which ends up being about 15%. All right. So it's really, this is a division problem. We know that there are 8,568 total groups that we can make out of 5. We could do Mohammed, Leo, Juan, Marta, Arthur. We can do Alicia, Joseph, Olivia, Simon, and Felix. And of these, the order doesn't matter to which we're doing. We're just grabbing any group of 5 people. Here, it was specific to the names with consonants. So there were 13. So we just have to do this as a division problem. All right. Same thing here. What's the probability that the 5 students' names end with a vowel? Combination of vowel, combination of no vowel. That's not going to matter, the 1. And so it's 792 divided by 8,568, which is our total. And so that's about 9.4%. All right, I hope this video helped. Good luck.